That. So about the deep neural network. Deep neural network is being like the, it's a subset of the neural network, okay? But normally in the neural network, okay, we just consider like one or two or at most a three hidden layer, okay? But mostly we just use a two hidden layer, okay? But in the deep neural network, okay, that network includes more than two hidden layer, maybe 3, 4, or maybe 100 hidden layer like this. Okay, that we call as a deep neural network. Okay, naturally, this idea is about the deep learning. Okay, last week I have discussed about the deep learning. Okay, deep learning is being normally for the machine learnings. Okay, you have to do one process. Okay, that is we call as a feature extraction. Okay, this has been you have to do like extract the information or useful input information to the machine learning. Okay, but in the deep learning, it's not like that. It's combined that two together. Okay, so we just send the raw. Actually, not the raw, but you have to do like normalization or something like that. First, you maybe you have to study about the cross correlation between input and output and cross correlation between the many input like this. Okay, after that, okay, you can send that data to the deep learning systems. Okay, it will do many processes including the feature extractions. Okay, any useful feature, it can be support to the final decisions. Okay, and then after that it will have similar to the normal machine learning, it has many other layers. Okay, and deep learning is the same. Okay, so deep neural network is the same. Okay, so instead of just a neural network, okay, we cascade many layers together. Okay, and then each of them, okay, they have their own different architecture. Okay, so that type of the architecture or the network we call as a deep neural network. It can model complex non-linear relationship. Okay, and the two well-known network. Okay, the first one is a RNN. Okay, today I will discuss today about that RNN. Okay, and then if you want to know about more today, you can add Piping. Okay, he's an expert in the RNN. Okay, it's used for the like it's very useful in the nowadays. Okay, because like uh, in the Google translations, Siri, and many smart application is based on that RNN network. Okay, it's used for like language processing, translation in many applications. Okay, and second, when no deep neural network is a convolutional neural network. Okay, convolutional deep neural network. Short is a CNS. Okay, and it's also very popular because it's used in the many image processings, okay, or image recognition, something like that. Okay, but in the deep neural network, there are many challenges. Okay, the first one is you have to train very complex or very large model. Okay, so you need the large data. Okay, and also for the hardware. Okay, but nowadays, okay, we have a very high speed computer, so the hardware is not the problem at that moment. Okay, and another problem, another challenging is a processing time. Okay, because this is very complex. Okay, when we train it, okay, it takes time. Okay, maybe 1 day, 2 day, or something like that. Okay, so the computational time is also the challenge. Okay, and another one is a overfitting. Okay, so anyway, let's continue with the one of the deep neural network. Okay, that is a convolutional neural network. Okay, so this convolution is been actually, you can see as a 2D convolutions. Okay, because actually in the neural network, okay, this is some kind of the convolutional calculation, okay, because you have to calculate the weight and then input like this, okay. But this convolutional neural network is mean the 2D convolutions. Mostly it's used for the image processing. Okay, so the convolutional neural network are based on the shear weight architecture of the convolutional kernels or filter. Okay, in this case, both of them 2D and sliding around the input feature like this. Okay, so in the convolutional neural network, okay, all the weight, okay, are composed like the kernel or filter. Okay, actually that's similar to the normal neural network. This is the weight, this is the weight, but it appears as a two-dimensional. Okay, and the application is, it can be used for image or video recognitions. Okay, or also the image captions. Okay, uh, the system will find what are the include in the image something like that. Okay, or image segmentations or natural language LLB. Okay, and then time series prediction also. Okay, there are many other applications also. Okay, so if you look at this image, okay, this cartoon, okay, this is a architecture of the convolutional neural network. Okay, so it's actually composed by the two part. The first one is we call as a feature map, or we call it sorry, in here, feature extraction. Okay, so this is our raw image. Okay, from this image, okay, it will pass to this one. Okay, and then how this part of the network is operated, they extract all the feature in the image. Okay, so in this image, okay, they trying to find out how many feet, head, and where is the eyes, and then something like that. Okay, they extract all the feature and also all the lines, something like that. Okay, and then they process on the two-dimensional data like that on the image. Okay, how they do it? They do the 2D convolution. Okay, from this image. Okay, so if you have this is like the RGB or GRB image. Okay, you may have many images like this, and then you will have like this kernels of filter. Okay, it will convolute on that image. Okay, and then generate another 2D image. Okay, and then from that one, okay, you have to do the convolution, 2D convolution again and again like this. Okay, and then first in each time, okay, you have to do the convolutions. Okay, and then after that you have to use the activation function, like similar to the normal neural network. Okay, to calculate the new value in the new image like this. And then you have to do this process, okay, this convolutional process again and again, okay, until we have the enough feature, okay. And also between the two convolution, okay, or after one convolution, it will be followed by another method that we call a pooling. Okay, so later on I will explain about that one. Okay, it's reduce the size of the data. Okay, and then after that is we'll do another convolutions and then boolean like this. Okay, and then finally after you have extract all the informations, okay, maybe you will extract this one, this one, this one, like this, important information. All of them will be fit to the normal neural network. But that is a deep neural network because you have many layers. Okay, that one we call as a fully connected layer. Okay, so in here, it doesn't classify anything yet. Okay, it just extract the important information or feature. Okay, and those feature will be used as an input to this neural network. Okay, that one we call as a fully connected layer, or sometimes we call it a dense layer. Okay, and then after that, finally, we can calculate the possibility of what is this image like this. Okay, so this is the basic idea about the convolutional neural network. Okay, so if I show you in here, in this CNN, okay, it's based by using the three layer. Okay, the first one is a convolutional layer. Okay, this is in this process. Okay, that convolution layer include the convolution operation. Okay, so do the convolution, and then after that followed by activation function like this. Okay, and then after that, some cases, okay, you can cascade two convolutional layer one after one. Okay, or some cases you can also separate it by pooling layer. Okay, this one is to reduce the data size, okay, or your image size. And then finally, all the feature will be sent it to this fully connected FC layer. Okay, and in the convolutional neural network, each layer increase the complexity by identifying greater portion of the image. Okay, so that has been the more important feature. Okay, each layer focus on the simple feature. Okay, so let's go detail about what is a convolutional layer. Okay, in normal neural network, okay, most of the computation is used when we train the model, okay, because we have to do backward calculation. But forward calculation is quite fast. But in the convolutional layer, it's not like this. Even in the convolutional calculation, it takes a lot of computational power. Okay, so that's why it's just like core layer of the CNN, and it's used heavy computation because you have to do the 2D image processing. Okay, so normally for the convolutional layer, it's composed by the three components. The first one is the input data. Okay, normally there's a 2D like the image. Okay, like this. Okay, so this is a 2D 1, 2, 3, 4, 5, 5 by 5 matrix. Okay, and then another component in that convolutional layer is a feature detector. Okay, that also known as a kernels or filter. Okay, this is like this. Normally that one is a small metric. Okay, maybe 3 by 3 or 4 by 4 or 2 by 2. Okay. Okay, and then inside the convolution layer, okay, this will do the convolution between these two 2D image. Okay, and for the 1D convolution, it's quite easy to calculate because like this is your data, okay, 1D data, and then this is your filter or your convolutional filter. You have to select this window, and then multiply weight and the data, and then S is there. Okay, like similar, like I mentioned, that it will be similar to the normal neural network. Okay, you have one weight, two, weight three. You have the data in here. You have to pass through the data in here. Each time, the data will be, each element of the data will be multiplied with the weight, and then send up, you will get the output. Okay, see, like this. But in the 2D convolutions, okay, you have to slide, okay, that 2D filter, okay, across there, this 2D image. Okay, so in the convolutional process, the filter shift by strike. Strike is being each time how many row, how many column. This filter need to move. Okay, and then you have to repeat it again. So you are, so this is being 3 by 3. So first you have to cover this 3 by 3 of the data first. Okay, and then after that, you will, if the stripe is just 1, you are going to move to next one like this. Okay, and then in the next die, we have to move like this. Okay, and then after that, we have to go down like this. Okay, so in the first place, in the red place, okay, in the red color place, okay, what we have to do is, okay, this is our data. Okay, this is our data, so 2, and this is our weight. So you have to multiply 2 into 1 plus this 1 multiplied with 0. So that is means 0 plus this 0 multiplied with this 2. It just means 0 plus minus 1 multiplied with 3. So it just means minus 3. Okay. 0 multiplied with 1 is 0 plus, sorry, minus, because 2 multiplied with minus 2 is minus 2. And then 0 multiplied with 1, 0. 0 multiplied with 2, 0. And minus 1 multiplied with 3, minus 3. Okay, so you will get this is 2. So 2 minus 2 cancel, and then minus 3, minus 3. So this one will be equal to minus 6. Okay, so from convolution of this red data with this filter, you will get the minuses. And then for this one, okay, after that, for this one, okay, for this one, you have to calculate all the elements, okay, within the green balls, okay, with the filter one by one, like similar to like this. And then you will get another one. And then for this one, okay, this is for the blue one, okay, you have to calculate this similarly, okay, like this. Okay, so that is mean you have to move this fiddle. Convolution is mean you have to move this fiddle around the image, okay, and then cover the whole image, okay, like this. And then in case if you use a 3 kernel like this, 3 different kernel or 3 different filter like this, 3 by 3, okay, you will get the 3 output image like this, okay, or 3D, sorry, 2D, 2D data like this. Okay, after that, like in this case, for the minuses, you have to pass through the activation function. And also whatever you got in here, you have to pass through the activation function, and then like this. And then after that, you will get the new 2D output. Okay, in here also you will get there another 2D output like this, and you will get there another 2D output like that. So this is one layer. Okay, and then for this output, you have to send as a input to there another layer like this. Okay, so what is that kernel or fiddle in here. Okay, actually that one is just detect or extract the feature from the image. Okay, one of the example, okay, use a lot in the image processing, okay, or computer vision CV is a edge detector. Okay, for example, like you can consider this one as an image. Okay, like maybe this is our image. Okay, okay. What we want to know whether this is humans or it's not good. Okay, human or animal. Okay, what we want to do is we want to know about the shape or structure. Okay, like this. To know the structure, okay, normally what we have to do is we have to draw just a edge. Okay, we don't want to know about the color. Okay, what we want to know is just a structure like this, like this. Okay, so we can know that this one is a human, this one is an animal, like this. Okay, so we want to know that only that structure. Okay, in some ism. So in that case, to get that structure, okay, we have to detect this edge. Okay, the edge is mean actually in the uh, image. Okay, it is mean the two area of the bezel. Okay, it changes of the bezel from the high or maybe dark to the bright color, something like that. Okay, and then if we consider in the bezel, okay, it will be like this. Okay, so this is mean one shade of the color. Okay, and this is another shade of the color. Right? If we consider this one, okay, so inside here, this is a dark color. Okay, and this one is a bright color or maybe white color. If we just consider only this part, okay, this is been like this. Okay, so from here, from this image, okay, what we want to know is that the shape, okay, I forgot, like the shape, okay, or just a structure. Okay, we want to know whether this is square balls or cycle or something like that. We don't need to know, we don't want to know this color inside. Okay, so that's why we have to detect this or we have to extract this edge. Okay, so if we want to extract that edge only, okay, what we can do is we can use the same special filter. Okay, that filter or that detector we call it an edge detector. Okay, it's quite simple. If we want to detect this horizontal color changes or horizontal line, okay, we can use the filter similar to like this. Okay, so this is 1, this is 0, this is minus 1. Okay, if you convolute this one with this one, okay, so let's consider about the first case, okay, for this one. So 10, 10, 10, from this side we got 30. If we multiply with 0, this is 0. Okay, from here, minus 10, minus 10, minus 10, you will get minus 30. If you add it then, you will get 0 in here. Okay, and then if you consider another locations, if that filter move to here, okay, to here like this. So in this case, okay, 10, 10, 10, so 30. So the middle one is just a 0. Okay, this one is all 0. If you add it, you will get 30. Okay, and then if move to the next slide, okay, like this. In this case also, okay, you'll get the color is not bright enough. Okay, let me use this color. Okay, so in here 30, 0, and 0. So you will get 30. And then if move to here, that is mean in that 3 column, okay, if their pixel value or their color is similar or same, okay, you will get 0 output. Okay, if there's a same changes from the high value to the low value, okay, you will get the positives like this, okay, and then if there's no more changes, you will get the 0. Okay, so in this case, so actually the H is in here. Okay, so we can detect this one. Okay, so let's say in the image, okay, actually what we just extracted this one, and then if we pass through this one, we can get this line. Okay, so that is been applied. Okay, by looking this one, okay, from the output, okay, we get just a structure of the shape. Okay, and also we can detect, this is for the vertical, okay, you can use this one, and also you can detect for the horizontal, or even you can detect like this one is changing from the high pixel value to the lower pixel value, and then this one also you can detect it, okay, from the 0, 0, 10, 10. Okay, this is from the lower to the higher, okay, but if you use this filter, you will get minus value in here like this. Okay, so that's why not only the edge, okay, and then we can also get the information about, okay, this is a high value and this is a low value like this based on this output value. Okay, and then if we want to detect the horizontal edge, okay, we can use this one. Or if we want to detect like this, like the corner, okay, for the corner, okay, we can use like this. Or that one. Okay. Maybe I think like this. Okay, so we can use the various detector or filter to detect, okay, just a edge. Okay, but in here, normally for the CV or image processing, okay, we have the fit value of this weight. Okay, fit value of the weight. You can use 1, 1, 0, minus 1, minus 1, or you can use like this. Okay, for example, 20, 20, 20, or minus 20, minus 20, minus 20. Okay, but for the whole process, you just use the fit value of the filter, the weight. Okay, but in the CNN, it's not like that. Okay, so for each filter, okay, so actually this is a filter, okay, or cuddle. This weight are not the constants, okay, but similar to the normal neural network, okay, we assign the random value, okay, and then we convolute here and then calculate the output, okay, and then based on the output, we have our target, okay, and then we find the difference, and then after that we update the weight like this, okay, because in the 2D convolution, okay, if we know the output, okay, this is our target, okay, this is our input, okay, we can find this weight, okay, to generate our desired target, okay, that is applied in the CNNs, okay. So in the 2D convolutional layer, okay, so as I mentioned in the previous slide, okay, this is our data, okay, and this is our filter, okay, and then this filter will convolute or move around the image, okay, and then this one will be our output for one layer, okay. After we got that value, okay, and then in here also, okay, we need to pass through that one to the activation functions, okay. But in the convolution, mostly we use a rectified linear unit reuse. Okay, but for this 2D convolutional layer, okay, normally we call as a partially connected. Okay, because if you look at in the fully connected layer in here or dense network, all the input nodes, okay, all of this or maybe all the next layer nodes are connected to the all previous layer nodes like this. Okay, for example, this one, okay, is connected to this one, this one, this one, this one, this one. Okay, so this output is contribution of all the input nodes. Okay, and this one output, okay, the output of this node is a contribution of the input from the previous layer like this. Okay, so this one we call it a fully connected or dense layer. But in the convolutional layer, it's not like that. Okay, each output, okay, has the convolution of only the input which are covered by filter like this. Okay, and for this one, okay, for this one, okay, it's include only the contribution of that 9 elements, not the whole input. Okay, and this one, okay, is contribution of this 9. Okay, so that's why it's not fully connected. So that's why we also call that one as a partially connected between the value in the input or element in the input to the output. Okay, and the filter weight are remain fit the constant in the convolutional or forward propagations. Okay, that is fit, but they need to be adjusted. Okay, during the training or back propagation, like similar to the normal neural network. Okay, so in the 2D convolutional, okay, there are 3 hyperparameters that affect on the value of the side of the output. The first one is the number of filter. Okay, if you use a 2 filter, you will get 2 output like this. If you use 3, you will get the 3 outputs like this. Okay, and second one is a strike. Strike is being when you move the fiddle in around the input. Okay, each time how many column or how many row are you going to move, or the number of the pixel that cannot. Okay, and that one is a whether you're going to use a 0 pattern or not. Okay, so let's look at each of them. Okay, but for the filter, it's like it's obvious. If you use a 2, you will get the 2 output similar to like this. If you use 3, you will get the 3 like this. Okay, so that is mean the number of the output will be multiplied of the number of the filter. Okay, and pattern is mean okay. Normally, if you want to, this is your original input, okay, and then you want to create the same side. Sorry, you want to make the output the same side as the input, okay. In that case, you have to add 0, okay, the outside of your input, okay, or the surrounding corner of your input like this, okay. And then in this case, if you do the convolution, because if you do the convolution, your input, like in this case, 1, 2, 3, 4, 5, 5 by 5. Okay, your output will be also 5 by 5. Okay, but you have to add 2 row of the 0, 2 column of the 0, like this. Okay, so you made it from the 5 to 5 by 5 to the 7 by 7 input. Okay, but this H is just favor the 0. Okay, but you will get the 5 by 5 output similar to your original input. Okay, and then if you don't use this 0 pattern, okay, your input will be 4 by 4. Okay, because in the first one will be covered to here, will be here. Sorry, 3 by 3. Okay, 4 by 4, 3 by 3. Okay, output like this. Okay, because same case that you don't want to reduce the image size. Okay, in that case you can use that 0 pattern. Okay, and another important parameter to consider is the stride. Stride is, as I mentioned, that whether it can be 1 or 2 or maybe more. Okay, so if 1 is mean, every time the filter moves, convolves over the convolve over the input, it just moved only one line or one row, one column like this. If 2 is mean, it moved 2 like this. Okay, if 1, you will get the 5 by 5. Okay, if 2, you will get the 3 by 3 like this. Okay, and another layer, okay, that's called as a pooling layer. Okay, this is also known as a tau sampling or counted dimensional reductions. Okay, it reduces the number of parameters in the input between one convolutional layer to the another convolutional layer. Okay, we just reduce the size of the output before we use as the input to the next convolutional layer. Okay, that layer we call as a pooling layer. Normally, that one put always between the two convolutional layer to reduce the size like this, from here to here, from here to here. Okay, it's reduce the size like this. So similar to the convolutional, okay, you have to do the similar calculation, okay, but there's no weight. Okay, in this case, kernel just apply for the aggregation of function to value within the species tree. Okay, so similar to the convolution, okay, we have the filter or the kernel like this. Okay, but we don't edit them or we don't do the calculation. Okay, what we do is the first one is a mass pool. Okay, for that case, we just find the maximum value. Okay, from that 9, or maybe if we use a 2 by 2, from this 4, which one is a maximum? We just transfer that one to the next layer. Okay, second one is we do send calculation. Okay, that one is just a average of that 9 or that 4 elements to send the output. Okay, like this. So actually, it will lost send information because we just, especially for the mass pooling, we just delete it. Okay, in here, this is like 100, this is 50, this is 40, this is 60. Okay, we delete them. Okay, we just send 100. Okay, but if you consider as an image, okay, you may not lose the information. Okay, because this is the most significant color of the pixel, and then we just maintain that one for the next layer. Okay, so that is mean you may lose accuracy, but you may not lose all the information. You still have that main information. Okay, but it's help a lot in the convolutional neural network because it's reduce the complexity. Okay, as I mentioned here, okay, from the big side of the data is what change to the smaller size like this. Okay, so it's help and also it's improve the efficiency and also it's mitigate the risk of the overfitting also. Okay, so this is the example of the pooling. Okay, in this case, this is mass. Okay, So mass is mean for this one, okay, if you look at this red color, okay, so the 7 is the largest, so we just write out 7, okay, and then, but it doesn't move one by one, okay, it will just move to the another 4 like this, okay, from here is 9, is the largest, so this will move to 9, and then it will move this 4, okay, so 8 and 4 like this, okay. But actually, this pooling is used a lot in the image processing, okay, especially if you want to scale down your image, okay, or like the in the not in the. And then after that, you got all the feature you want, okay, and then we have to send that one to the fully connected layer to do the classifications. Okay, so all the classification process will be done in this network. Okay, so as I mentioned, that this one is just to extract the feature. Okay, with information with feature importance. Okay, and then based on them. Okay, so this is all the feature. Okay, based on them, the fully connected layer will be classified. Okay, what is this image? Okay, so perform the test of the classification based on the feature extracted through the previous layer and their different filter. And then after that, it need to be fit, or it need to be set to this fully connected layer. Okay, this is like normal neural network, big neural network. Okay, before that, this is a two-dimensional, but this one is input is a one-dimensional input. Okay, there's a one layer. Okay, that layer we call as a flattened layer. This is been from the 2D. If we have 1, 2, 3, 4, okay, we convert it to the 1D. 1, 2, 3, 4, like this. Okay, that process we call as a flattened layer. Okay, but there's no complex computational layer in here, so that's why we don't emphasize on here. Okay, this is like the conversion from the two-dimensional to the one-dimensional data. Okay, and then finally, as a output of this one, use a short-net activation function. Okay, but in here, okay, it's depend on the user side. You can use any other activation function, but for the final output, okay, we have to use a short-net. Okay, because we have to differentiate. But depend on your application, you can change other also. Okay, in this case, we just for the classification amend many class. So that's why we use a short-net activation function, and then we can calculate that. We can classify what is this anime. Okay, like this. So let me show you some calculations. Okay, of the new CNN network. Okay, because in the trainings, okay, that similar to the normal standard neural network. Okay, you have to do two direction. Okay, the first one is a forward. It's just like the same as when you predict or when you do the testing. Okay, but in the training, after you finish the forward, okay, so this has been your, okay, so this is your model or your network. Okay, so you have the input fatal I, and then for that one, okay, you have the output, okay, that requires a target. Okay, so this is our data set to train the model. Okay, as first, the model haven't trained yet, so this has been modern, doesn't have any knowledge about the data yet. So how we do it, we have many pair of the input and output. Okay, we send that input. Okay, and then we have one predict value. Okay, and then we find the difference between our target and our predict, and then we calculate the error that I have mentioned in the last week. Okay, based on this error, okay, we are going to adapt, or we are going to change the weight in the mode. Okay, so anyway, to get this predict value, okay, we have to do the forward propagation first in the CNN also, right? Similar to the normal neural network. Okay, and then after that we got the output, and then we find the error. Based on the error, we need to update all the weight. Okay, so in this case, to be differentiate between the normal neural network weight and CNN weight. Okay, let me write down as a F F F. Okay, so this all of the F are weight value in the filter. Okay, and this is our input. Okay, if this is an image, this is the pixel value. Okay, so in the forward propagation, okay, what we have to do is we have to do the convolution like this. Okay, convolution like this. So that is mean we have to do convolute input with the filter. Okay, and this one is a 3 by 3. This is a 2 by 2. So one is in here. Based on this red balls and fiddle, we will get the 011. Okay, like this. And based on the element inside this green balls, okay, we got this 012. Okay, multiplication of each element from here to here, from here to here. Okay, and then similarly, we have to calculate. Okay, for that red or black balls. Okay, we got this one. For here, we got this one. Okay, so in the computer, okay, if you use MATLAB or the Python, okay, you just use the function of the convolution 2D, okay, and then H F, okay, you will get the output, okay. But to understand about the backward propagation, okay, let's consider for each output, what are the contribution, what input are contribute to the each outputs. Okay, so let's consider this one, O11. Okay, for the O11, okay, what we have to do is for H11, we have to multiply with F11, right? So this is mean this one plus H, let me write down H first. H11, F11, okay? But this one is easy to write because for the subscript, okay, they are the same. Okay, H12 multiplied with the F12 plus H21. We have to multiply with F21 plus H22. We have to multiply with F22. Okay, so that is mean for the O2, okay, it's contribution of all the weights, of course. Okay, but for the input, not all of them, this partial, okay, only the contribution from H11, H12, H21, and H22. Okay, and for O12, okay, for the O12, let me change the color, the green color. Okay, so for this case, for H12, okay, we have to multiply with F11, and H13, we have to multiply with F12 plus H22 like this. Okay, for H23, we have to multiply with F22. Okay, so similarly, that color. Okay, for O21 also, O21 is this one. So maybe to be the easy, let me write all the A's first. Okay, and for F, they are the same. Okay. H22 plus H23 plus H32 plus H33. Okay, for the F, the same F11, F12, F21, and F22. Okay, so please be noted that for each output O, okay, have the different element of input, okay, like this. So based on this equation, okay, for the backward propagation, okay, similar to the normal neural network, okay, so this is mean you can consider like even for the 2D, we can consider as a 1D. Okay, so what we have to do is from actually let me consider like this. Okay, so this is the first. So this is our input. Okay, H1. Okay, convolute with this is convolute. Okay, this is convolution. We have F1. Okay, F1 is mean the kernel for the layer 1. Okay, we have O1, and O1 is the same as H2. Okay, and then after that we pass to the another convolution with F2, and then we have O2 is equal to H3 for H1. Okay, so this is mean layer 1, this is 2, this is 3. Okay, so in this case I just skip the pooling layer. Okay, but actually please notice that there's a pooling layer in here. Okay, but pooling layer is been no calculation. Okay, just we pick at some value. Okay, so that's why we don't need to consider for the gradient. Okay, so this is mean O3 will be A3. Okay, each of the output the output from the each convolution will be passed to the next convolution like this. Okay, and then in this case we just consider only one like this. Okay, this is the 8, this is our input. Okay, and this is our feeder weight. Okay, and then this will generate the output. Okay, and T in here we have the fully connected. Okay, and then we have the Y. From this Y cap or maybe H, okay, we can calculate the error or we can calculate the loss function. Okay, based on okay, let's say this is the error. And then similarly as in the normal neural network, this error need to be sent back as a back propagation. Okay, so this error is actually okay, we have the loss functions, okay, L, okay, we have the L. I will not redefine about the L. L is the loss functions, and then the error is actually from here partial derivative of whatever, okay, the output. Okay, so in here, let's say this is O3. Okay, and whatever O in here. Okay, the last one. Okay, so we move that error to here, 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 and then finally is where appear in here. So this error is, let's say, partial derivative of L divided by partial derivative of O3. Okay, and then this error we will move back to here like that. Okay, so anyway, this O, okay, the O is output of this layer, and then this is calculated the convolution of A, and then we transfer this one to the next layer like this, and then we got like this, and then we have the error, and then that error, okay, when we move back to the next one, okay, next one like this, okay, and then in here we will have, okay, this one, and then in here we will have partial derivative of L with the respect to O2. In here we will have partial derivative of L O1 like this. Okay, so this is similar to the neural network. Okay, so in each layer we have the error contribution of partial derivative of L. L is mean loss function. Okay, it's depend on the what type of the loss function used. Okay, with respect to the less outputs. Okay, and then this one we can send to here by using the chain rule. Okay, from here we can calculate the partial derivative of L divided by partial derivative of S. Okay, it will be equal to chain rules. Okay, is equal to like this. Is equal to G multiplied with G A like this. Okay, so similarly, actually this O is calculated based on the A's. Okay, in this case, O is actually multiplication of ON, sorry, A's and F. Okay, so that's why, okay, if you want to calculate the partial derivative of L with respect to A's, we can calculate partial derivative of L with respect to O first. Okay, O is mean actually from here, multiplied with the partial derivative of O with respect to A's, like this. Okay, so in this case, we can transfer that error. Okay, not only because there are two ways. Okay, each time we have the weight like this, and then we need to update the weight, and then also we have to transfer that error to the next layer. Okay, so that's why we have to transfer to here and also transfer to here, to F and to A's. Okay, so similarly, when we calculate the partial derivative of L with respect to A's, we have to calculate the partial derivative of L with respect to F. Okay, but they're the two calculation we have to do separately. Okay, but this one is to update. This one is to update the weight. Okay, but this one is to propagate or to transfer the error to let's be say the previous or the layer before, like this. Okay, so in here let me emphasize this one first. Okay, and then after that I will explain about this one. Okay, so we assume that we already get the partial derivative L with respect to O. Okay, O of this outputs, we got this one. Okay, but what we have to do is we have to find this one and this one. Partial derivative of O with respect to A's, partial derivative of O with respect to F. Those are called as a local gradient. We have to find that two separately. Okay, so before we consider about that local, we have already considered the output from there forward calculation. Okay, O11, O12, O21, and O22. Okay, and then this is a function of F. Okay, all the O are function of F in here. Okay, so we can calculate each O with respect to each F like this. Okay, so in this case, if we have 4O, okay, and then we have 4F, we have to find that local gradients. Okay, there are 4 into 4, 16 local gradients. Okay, but actually in here it's quite simple. Okay, because if you look at here, this is O11. Okay, and then we will find that O11 with respect to each F first. Okay, so for O, we have to find 4 times or like this. Okay, so in this case, O11, so this is the O11. If we differentiate this O11 with respect to F11, okay, so this one, you will get the H11. Okay, this one 0, this is 0, this is 0, like this. Because there's no F11 in this stem, no F11 in here, no F11 in here. So they're all the constants. Okay, so you can write this. And then if we differentiate this O11 with respect to F12, okay, so there's no F12 in here. So this is 0. This is not 0. So in here, H12. Okay, in this case, 0, 0, like this. Okay, so similarly, if we differentiate with respect to F12, we will get H21. Sorry, F21, you will get H21. In this case, you will get H22, like this. Okay, so similarly, you can calculate this one also. 1, 2 with FF. Okay, what you will get is H12. Okay, you will get H13, and then this one you will get H22, and then from here you will get H23, like this. Okay, so similarly, okay, if you respect this one with the East F, okay, you will get H21. Okay, if you differentiate with respect to F11, if you differentiate with respect to F12, you will get H22, and then from here you will get H31. In here you will get the H32. Okay, like this. For O22, if you differentiate with respect to F11, you will get H22. If you differentiate with the F12, you will get H23. You will get H32, and then you will get H33, like this. Okay, so this is, okay, partial derivative of each O. Okay, each O. So I is, in this case, 1, 1, 1, 2, 2, 1, 2, 2. Okay, with respect to if I. Okay, like this. Or maybe we can use a different K and I, like this. Okay, so this is our local. We can find that one easily. And then if we find partial derivative of L with respect to each F, okay, it will be equal to summation of K equal to 1 M. Okay, so in this case, K is like over that 4. Okay, and each O, okay, each O is output because you will have 4 output in here, and then for this you have to do the partial derivative with respect to each O, okay, O11, O12, O21, O22. And then each O, you have to do the partial derivative with maybe F11, okay? And then after that, you have to do the same summation for the F22, F21, F12, all of them like this. Okay, in this case, let me show you one example. Okay, partial derivative of this one L with respect to F11. Okay, so that is mean for the F11, if you look at this three, sorry, this four, all of them include the F11. Am I right? So that's why you have to write down partial derivative of O11 like this, O12, O21, O22. Okay, and then after that, O11 with respect to F11. That is mean H11. Okay, so in this case, I can write down like this. Okay, multiply with H11. Okay, plus O2, sorry, O12. Okay, for this one, okay, if you differentiate with respect to F11, okay, you will get there. Sorry, 1, 2 here. You will get there H12. Okay, plus 2, 1. Okay, this 2, 1 with respect to F11, you will get the H21 like this. Plus, okay, H22. Okay, so this is me. I just copied this H value in here. Okay, so similarly, you can also consider sorry, F12. Okay, this will be equal to O11 and 11 with respect to F12. This is mean H12 plus O12. So this is mean this one. Sorry, this is 1, 2. Okay. H13 plus O21 H. This is mean this one. H22 plus H23 like this. And then similarly, you can find for the other. Okay. So finally, you will get like this. Okay. If you look at this equation, okay, if you look at this equation, so this is O11, H11, O12, H12, O21, H21, O22, H22. Okay, and then if you look at this one, O11, H12, 13, 22, 23. And this is 21, 22, 23, but this O is the same in like this. Okay, but this is mean like the convolution. Okay, this is like the first operands. Okay, this is the second operand. Okay, this second operand is just convolute. Okay, it moves around. Okay, if you look at this calculation detail, okay, this is like the convolute. Okay, or we fit this one and then we convolute like this. Okay, so that is mean this is a convolutions. Okay, and then if you convolute your input, this is your input, and this is error from previous layer. Okay, to get this one, okay, actually this is like similar to the sigma. Okay, to get this one, what you have to do is you have to convolute with the input. This is your input for that layer. Okay, this 8. Okay, from here you have this partial L, partial O. Okay, if you convolute that one, you will get this metric. Okay, you will get this metric. So we can use this one to update, okay, to update for the weight in the east element. For the F11, okay, we can calculate F11, okay, so that is mean the next one, this is the current time, plus alpha, this is mean the learning rate, multiply with the F11. Okay, similarly for F12, okay, this is current, this is, I'm sorry, this is Nate, this is the current, plus alpha, partial derivative of F with respect to F12, like this. Okay, so basically this one is, okay, if we consider in the matrix, okay, we have okay, this is F11, F12, F21, F22. This is for next iteration. Okay, and then this is F from the current iteration. Okay, this is from the D. This is from the D plus 1. Okay, we have F11, F12, F21, and F22. Okay, plus alpha. Okay, alpha is just a scalar like this. Okay, so this means you can calculate this one by this convolutions. Okay, the error from the previous metric, error from the previous layer, convolute with the input, you will get the error or the update information of the weight for this layer, and then you can update it, you will get this one. Okay, similarly, you need to transfer. Okay, so because this one we got it from the previous one. Okay, because this is appear as an ace in ace. Okay, this partial L by partial ace, okay, will be similar to this one. Okay, so let's say this, if this is D, this is 90, so this is from D plus 1. Okay, and then you have to transfer this one to here for the next layer. Okay, like the contribution about backward propagation. So you have to calculate this one also. Okay, partial derivative of L with respect to ace. Okay, this will be equal to partial derivative of L with respect to O, that is mean this one, multiplied with this local gradients. Okay, O with respect to ace. Okay, so similarly, in the previous calculation, okay, we differentiate with respect to F. In this case, we have to differentiate with respect to ace. Okay, so that is mean if you differentiate this O11 with respect to H11, we will get F11. Okay, and then for this case, we will get F12, F21, and F22 like this. Okay, and similarly in this case, we can differentiate like this. H11. Okay, but it's equal to 0 because there's no H1 here. Okay, and if we differentiate with respect to H1, 2, okay, is will be F11. Okay, you can calculate like this. Because for the A's, okay, we have 1, 1, 1, 1, 2, 1, 3. Okay, 1, 3, we will get F1, 2. Okay, but in this case also, actually, you have to differentiate with all the A's. Okay, 1, 3, you have to find this one also. Okay, you have to find this one. Sorry, not that. 2, 3, and all for the 3, all for 9. Okay, but for this O11, okay, it have the contribution of H11, H12, H21, H22. For the rest, no contribution, so that is means 0, 0, 0. Okay, similar in here, okay, each of them have the contribution only 4. Okay, so that's why we got like this. Okay, and then you can calculate for other thing also like this. Okay, and then if we calculate this one, partial derivative of L with respect to H11. Okay, you have to calculate similar to the previous one. Okay, for that L, you have to calculate for the all K. Okay, in this case, K is the same. Okay, K is belong to 1, 1, 1, 2, 2, 1, 2, 2. Because we have only 4, 4. Okay, so that's why K have 4. Okay, and for each of them, okay, you have to consider that O with respect to that A's you are going to find. Okay, so in this case, partial derivative of L with respect to H11, okay, is will be equal to, okay, but for H11, if you look at here, the H11, okay, it will contribute to the O11 alone. Okay, in the O12, there's not H11 included. Okay, and O21, okay, H11 does not include, and O22, H11 does not include. Okay, so H11 is included in O11 alone. H12 include in the O12 alone. H31, okay, H31 contribute to the O21 alone. H33 is contribute to the O22 alone. Okay, but for H12 is contribute in the which one? O11 and O21, but not, sorry, O12, not in the O21 and O22 like this. Okay, so basically from here we can say that 11, 13, 31, 33, okay, is what include in only one O, okay, but for 1, 2, 2, 1, 2, 3, and 3, 2 is what include in the 2 O, okay, but for H33, sorry, H22 is what include in all O like this, okay, so that's why if we consider about the partial derivative with respect to H11, okay, it's include only to the O11. So we have to consider only O11, okay, and then the O11 partial derivative of O11 with respect to H11 is just a F11. But H12, okay, for the H12, is included in the O11 and O21, okay. So that's why O11 and O21, and partial derivative of O11 with respect to H12 is just mean F12. And this one is, where is this? O12 with H12. This is mean F11 like this. Okay, and then you can find for the all the A's. Okay, partial derivative of L with respect to all the A's like this. Okay, so in this case you have only one. This have two. Okay, like this. And then this one also, okay. Actually, this is mean also the convolutions. Okay, convolution between what and what? Convolution between, this is the error from the previous one, similar to the, this is mean the fatal. Okay, convolution between the fatal and that error. Okay, propagation of the error from the previous one. Okay, but for the fatal, okay, not in the same position. Okay, what you have to do is you have to rotate this one. Okay, rotate here to 180 degree, we call it. Okay, so that is mean this F22 have to move here first, 90 degree, like this. Okay, this one also move one time, two time. This will be moved to here, two time, like this. Okay, so this is the fatal, but we have to rotate it 180 degree. Convolute with the error, we will get this one. Okay, and each of them will be appear as a error propagation from the previous states, like this. Okay, like this, because is from the let me write like this. Okay, H from here is the same as O for previous one. Okay, so like this, and then we can use this one for the next layer and next layer and next layer, and then finally we can calculate all the weight. Okay, like this. So this is about the back propagation about the neural network. Okay, so it's already says. So let me stop in here about 15 minutes. Okay, and then after that we will discuss about the recursive neural network. Okay. Okay, let's about 10 minutes. 10-minute break.